to a stop sign, you got a couple ways to stop, right? You're going to take the mass of your car and you're going to change its velocity. If you apply a large force, the stopping time is very small. But if you apply a small force, the stopping time is very large.
And it's the force of friction created by the brakes.
Sure. So this so if I have the same MdV, you can have a large force that stops in a small time, or you can have a small force that stops in a large time, right?
Yeah.
Is that cool? This also says, like, if you have contact, right? If there's contact, there's always a problem that shows up on the test.
Have you ever been like, I was backing into a spot today, and Annalise Lechner was backing in next to me, and like I pulled in and I finished pulling in, but she started moving forward, and like out of my peripheral, it looked like I was still moving, and I freaking slammed my foot to the floor because I panicked. I had a full-on panic, and I was like, why is my pedal not working? I'm like, what the heck?
I just did that the other day too. Like it still happens.
My car has 12,000 miles, and my brakes already going to the floor. I didn't think I'd beat on it that hard.
What car you got?
This is a Civic.
Honda Civic.
Here's a problem that you need to be aware of. Okay. So this tennis ball is going to come in. It's going to hit the wall. Right before it hits the wall, it's moving at 20. It bounces off the wall. It's moving at 15 meters per second. Is that cool? The mass of the tennis ball, they're about 100 grams. We'll call it 0.1 kilograms. Is that cool?
Yeah.
And we're going to say it's in contact with the wall. Okay. It's in contact with the wall for 0.02 seconds.
Oh, and then you can find the force that is applied because you have the mass, your change in velocity, you have. Okay, is this equation we can use on the AP test?
Yeah, so you need this to solve this problem.
Can we just
Can we
use
just
it?
throw that on the page, or are they
Well,
gonna?
it's not-
So it actually comes from here, so if you just jump to here, that would be fine. And this is gonna be a multiple choice also, so you're here. Now, I don't want you to miss this. You have the mass, you have the time, we're gonna solve for the force. You gotta figure out the change in velocity is. Check with your neighbor, what do you think the change in velocity is? I'll give you a hint, it's not 5.
Yeah, it's 35.
It's not 5.
Is it
It is fine. I mean,
No, it has to be
yes.
35, because
Yeah,
15, because its velocity is a vector and it's going the other way.
Right,
It's
yeah,
20
yeah.
minus negative 15.
Oh, velocity is a
so-
vector, remember that.
Yeah, so I told you that the speed was 20 and 15, but the velocity is negative 15. See how cheap that is? Okay? So when you go to plug and chug this, I have the force times the time was 0.02, the mass is 0.1, and the change in velocity was 35.
And I bet you one of the answers will be solved.
Oh, absolutely. Absolutely.
Because they're little jerks.
Is that all right?
Right.
So let's pull this out again. This is also, you also already recognize this. You may not notice that you recognize it. But what happens if I divide both sides by dt? What's dv dt?
Why do you have so much energy? It's 8 o'clock.
Listen, man, I'm just clapping, man.
So you see how this is dv dt is the acceleration, right? So this form here allows you to like move within these dynamics kind of understandings.
I'm definitely gonna like, when I get my equation sheet, mark it up right away, like spend 2 minutes just marking it up with a bunch of like little things so I can fly through stuff.
Mr. Betta.
Yeah.
So was that final minus initial velocity, or did you just,
Yeah.
and you just like got rid of the negative?
Oh, so that's actually a great question. So in my head, I skipped a step. So the question is, which hits harder, the ball on the wall or the wall on the ball?
They're equal.
They're equal. So what I ended up actually solving for here was the force.
Okay.
It's both the force that the ball exerts on the wall and the wall exerts on the ball. And then since they're the same size, they have the same magnitude, I got rid of the negative sign because we were just calculating the force, which was kind of the absolute value.
So would they like, that be like a 2-questioner, like which one has a greater force and then solve for the force?
No, yeah, actually, they could, but it would be specific, what is the value of the force, and they would either say that the ball exerts on the wall, which would be a positive force because it's pushing it to the right, or if they said, what is the force that the wall exerts on the ball, then you'd have to know that that's left, that would be a negative.
So you have to use your brain power and think about all those.
You gotta read the question,
Yeah,
right?
and I suck at reading.
Same.
That's-
Step one.
Well, just remember, like RTFQ, read the full question.
Whatever you say, man.
RTFQ, just
I
read
just look at the
the
pictures.
full.
What was it?
Yeah.
We were doing an AP Calc
Wait, there's one
thing,
without a picture. I just-
and, well, we were doing AP Classroom with Mr. Smith was out, we were watching notes videos, and the first thing she said, step one, understand the problem. And I was like, yeah, no, no, blank.
So the impulse equal to F dt, what does this say to you? This has got to speak to you, what's it telling you?
Joule, energy, joules.
Not joules.
Oh, wait,
Not
what is
joules.
that?
Not
I did it again, what is it? Lowercase j is a joule.
No, uppercase J is a joule, but it's a unit, not a variable.
Oh, yeah, LOL.
What is this J?
That's a.
Impulse.
Is the impulse.
Impulse.
What does this tell you to do?
And I do.
Okay, so if you have an equation, you gotta take the antiderivative.
Or the area under the curve.
We take the area. That is correct. So if you were given something that looks like
You
this,
said they had a double header.
Oh, yeah.
They have a
the
doubleheader.
playground thing.
Yeah, his parking lot's like full.
Norris baseball right now.
There's also a play going on.
I saw Miss Petta at the
Yeah.
softball. Pretty cool.
she's awesome. So the area of this
I would hope you think
is
so.
your impulse, right? What are the units?
Joules, no.
It's,
Newton
Seconds.
seconds.
Mm-hmm.
nice.
Air high five. Oh, left me hanging.
Now, what is this equal to though? What does the impulse do?
Something. Oh, it's the, it's what changes the, God.
It changed the momentum.
Yeah.
That's absolutely what it does. The impulse changed the momentum, and you can see, that's what's on there, right? Keep in mind that because the force is a vector, impulse is a vector, and the change of momentum is also a vector.
It's because, and then force changes.
Yeah, whatever net unbalanced force you have that changes the momentum of an object is going to change the momentum in the direction of the change, or in the direction of the impulse.
So is impulse and force, what is the difference though?
What's
I'll be
that?
right.
Because the force itself, okay, the force itself isn't enough, the force has to last for some time. It's this same thing here, like, if I want to change the momentum of an object, I need to apply a force, and that force needs to last some time. Whether you apply a large force over a small time, or a small force over a large time, or a large force over a large time, both matter.
And that force over time, or change in time is impulse.
Yes.
So if I just apply a force for no, it's not essentially.
But if you applied a large force, if it's a small time, the change in momentum is going to be small. If you want a large change in momentum, you're going to try to maximize both force and the time that that force is applied. It's like the hump. Like the area that we colored is the change in momentum. It's the impulse. How do you get a bigger area?
You either add more force, or you can
Yeah.
add more time.
We're going to make the hump bigger, and we're going to make it over a longer time. You can see the area is more. Is that cool? What's next? Oh, P is equal to MV.
I think we get that.
We're good. I feel like we're good there. I feel like we're okay on that one. Okay. The next one says that if you have two objects, two surfaces that are sliding against one another, and whether they are attempting to slide against one another or they're actually sliding against one another, okay, there might be an anti-sliding force between the two surfaces, right?
Which is Friction,
which is the frictional force. How do you solve for the frictional force?
something.
So that,
Oh, it's
you
oh,
roll
it's just the
that.
coefficient of friction
Times what?
force, or force.
No.
Times the normal force. Remember, it's by increasing the surface-to-surface contact, right, by making them press harder against one another, you're going to increase the friction between the two.
Why do they use greater than
So,
or less than?
this is actually interesting. I can't remember if we did this or I just wanted to do this. So if you put a block on a ramp here, let me try to draw it again. I need it to just be one.
Oh, I think we did this one, and then you tilted up more and
Yeah.
more.
So as you start to tilt it, at some point it's going to go, right?
But the normal force is always going to stay this.
So the normal force actually decreases as you rotate it. Okay? The normal force decreases as you rotate it. But the frictional force, right? Let me use a different example. That one's not going to work for us. Let's do it this way instead. So if I start pulling on this object, if I just pull with a little like 1 Newton force, is it possible it's not going to go? Let's say it's not going to go. Doesn't go at all. How much frictional force is there?
Well, at least one.
It's 1 Newton,
Oh.
right?
Well, yeah.
Oh yeah, because they're
It's not going anywhere. So the frictional force is equal to 1 Newton. Is that cool? Now I'm going to pull with 2 Newtons, and guess what? It still doesn't go. What's the frictional force now?
2 newtons.
Now it's, ooh. What are you doing now? 2 Newtons. All right, if I pull with 3 Newtons, all right, it's going to start to slide. So the thing is that the frictional force isn't necessarily equal to, right? Is it less than? Yeah, less than or equal to this thing here. So, because the frictional force is always a reactionary force. It's reacting to the external stimuli here. So it's going to be less, it's always going to be less than or equal to the maximum value of that coefficient of friction normal force. So it could be less if the pull force is less, but it can never be greater than that threshold.
Oh, right. Because then it becomes
Then it
not
starts to
static,
slide.
but.
Yeah, then it just goes to kinetic friction.
Yeah.
Okay? Feel good? Feel smarter or no? You'll notice in the equation though, this is actually really interesting to me. I don't know if it's objectively interesting. They have absolute values over those. What does the absolute value do to a vector?
It makes it positive always.
Yeah, so it makes it positive, but it removes the directionality completely.
Right.
See, this is just a number, it would be a scalar. So without the absolute values, it would imply that these two vectors are in the same direction, right?
Oh, but that's.
But they're not, because which way is the normal force?
No.
It's up, and if you're pulling this way, the frictional force is, these are actually always perpendicular to each other. So you need to use the absolute values here, which takes out the directionality.
Yeah.
That's not super necessary for you to know that, but it's kind of like your understanding is sophisticated enough to understand it now, to get it now.
It just makes it look less complicated. I'm shooting at you.
Now we know. Delta E, what is that? What do you think the delta E is?
That's just work, the change in energy.
Good, so if you're gonna change the mechanical energy, right, that's the work. And how do you calculate the work?
Force times distance, the interval. I really love it.
Now, they use dr because I use dx, and the x means any direction. They use r, which is kind of a better indicator that it's any direction, but I feel like sometimes that gets confused with the radius if you don't know that r is just an any direction vector.
I think we need more letters.
Alex, it's late.
What?
Dexter had a scrimmage, and he's getting home kind of late. No big deal. Is this cool? So what does this tell you? It's speaking to you. What does it say?
Saying as this,
You take the area to get the work.
Absolutely. If you have a force distance function, okay? If you have a force distance function, then the area is the work done. Now, a moment ago, we were talking about I took a different area to get the impulse, but what was that? How was that one different?
It was force and time.
That was force time, right? That's the difference between these two ideas. One is the force displacement, the force distance, the other is the force change in time. Is that cool?
Mhm.
If you do some work on an object, can you change the kinetic energy of the object?
Yes.
Yes, you can. How do you solve for kinetic energy?
Can you perform that from this group? I think I understand that.
That one's not a tough one. What's the next one?